And so lastly, I just want to give a couple of tips for good graphing habits. It's very easy to make a graph that kind of trips people up or gives people the wrong idea, when in reality, statistics is all about allowing people to take in and process information to come to correct conclusions. So 3 things you want to be on the lookout for when you're seeing graphs in daily life is improper scaling, bad interpretations of the graph, and also 3D graphs. I'll kind of get a little more into what that means in a second. So let's look at some bad examples of graphs that I've been able to pull from online. This first one on the left, you might be able to tell right away what's wrong with it. It's that pie charts are always supposed to add up to 100%, but for some reason this one adds up to much more than 100%. Obviously that doesn't make any sense. Whenever you make a pie chart, always check to make sure that your percentages sum up to 100%. Now the 2 graphs on the right here kind of illustrate this problem I was talking about with 3D graphs. And it's this idea that when the bars you use, or whatever image you use to represent the bars in a bar chart or histogram, it's when you change both the length and the width of whatever it is you're using. And we can see that in this case of the Halloween candy collected. If you just look at this graph really quick, you might think Michael collected 4 times as much candy as Shayna, because his bar, in this case, his candy, is 4 times the size of Shayna's. But if we look at the actual y-axis, which tells us the number of pieces of candy they collected, you see that the difference is actually only about 18 for Shayna and about 36 for Michael. So it's actually only a 2-fold difference versus a 4 times or 5-fold difference, which you might conclude by looking at the graph. And the same problem arises in the one right below it too, with ticket prices to baseball games and basketball games. You can see that the little baseball only goes up to $10 and the basketball goes up to $50. So this graph does tell you that basketball games in 2001 were significantly more expensive than baseball games in 1991, but you might think that difference is really 10 times or 20 times just by looking at the graph without looking too closely, as opposed to the 5 times difference that it actually is. And 2 more examples they have that represent other poor graph making. This one on the left is probably my favorite. It's the number of gun deaths in Florida, and the graph tells you the number of murders committed using firearms. And so something that's really weird about this graph is traditionally we have a graph that starts at 0 and goes up with the count. But this one actually starts at 0 at the top and goes down, which is very strange right off the bat. And so this is clearly a way to kind of deceive the audience. This graph was made in mind to show that the Stand Your Ground law enacted in 2005 was reducing the number of gun deaths in Florida. Because people are going to look at this graph, they're going to say, oh, in 2005 this point was here, but then as soon as this law was enacted, it goes down to here. And the other thing people are going to look at is they're going to look at this 873 and then see this 721 and conclude, wow, things have gotten better. There are fewer gun deaths. But in reality, all of the decreasing in gun deaths actually happened before this said law. You can see here it's at about maybe 550, and actually after this law was passed, gun deaths went up a lot. In fact, at one point, you can see here, they went almost back to how they were at the start of this graph. And so it's a very deceiving graph to kind of get you to believe one thing when in reality the data might tell you something different, and you just always want to be diligent when looking at graphs. And then this last one, this one is again pretty egregious. It's just an example of bad scaling. We see that this very tiny bar here represents 6 million, and this really large bar, which is about triple its size, is 7,066,000. And you might look at that graph and go, wow, there's been an incredibly large change from one to the other, from March 27th versus the March 31st goal. But in reality, there hasn't been that much of a difference. The reason it looks so amplified is because this scale must be starting at something like 5 million. Or maybe even something bigger, probably about 5.5 million. It makes this 6 million look much smaller than it actually is. And you just want to be on the lookout for that. And so, in conclusion, some tips for not deceiving or misleading other people with your graphs is to stick to those 2D charts, stick to those rectangles in your bar graphs and histograms. Don't make them go wider or narrower in width. Use a linear scale when possible. Sometimes the numbers will change really fast and you'll be forced to use a logarithmic scale, which we'll get into in some future video. But in general, stick to a linear scale. If something is twice as large in count as something else, the viewer should be able to see that and it should look twice as big as the other category. Order your bars sensibly. Just going back to relative frequency, when you graph relative frequency or any bar chart, if the numbers have a quantitative context, like in this case the number of ducks taken from the park, you want to make the bars go 0 to 2, 2 to 4, 4 to 6, and so on. You don't want to order it from 0 to 2 and then skip to 8 to 10 and then go back again. You want to make sure they're in the proper order. And lastly, don't report false conclusions. You want to be really careful and not say anything that might not be true, because with statistics we can't prove something is true beyond a reasonable doubt usually. There's no absolutes in statistics. And tips for not being misled by a graph is pay attention to that axis scaling once again. This is a really good example of it. Is the source credible and or impartial? We can see down here gives us the source, the Florida Department of Law Enforcement. It's very possible that might be a biased source in terms of gun deaths. And lastly, how is the data collected? Oftentimes you won't have the answer to this question for every graph or plot you see, but we want to know, how is the data collected? Did they leave out certain elements of the population that they were sampling from? And were they right to do that? Do they disclose that in the graph? How you collect the data is just as important as how you interpret it in the end. If your data is bad, then your whole graph is off and you can't really come to any conclusions at all. And so that's about it for this video. And next time we will take a look at how to read histograms and be able to take the most important information from them.